Hello, guys. This is team 2, and we are presenting about HVAC in vehicles. In our team, we have Usman Akram, Luciana, Stephen Lucas, Gwen, and myself, Anas. Next slide, please. Next slide, please. All right, and here are the draft outlines. We have first, we'll be going through introduction, followed by background, motivations, objectives, references, and then finally the appendix slides. Next slide. I'll pass it to Luciana for introduction.
HVAC stands for heating, ventilation, and air conditioning. The basic principle behind the operation of an HVAC system are conduction and convection. HVAC systems are used to provide a comfortable environment and circulate air in vehicles. The purpose of HVAC system is to add heat or remove unwanted heat from the passenger cabin. The driver can control the system either automatically or manually. The system works on the principle of thermodynamics, heat transfer, and fluid mechanics. Next slide, please.
The first heat exchanger was patented for the first time in Germany in 1878. The invention, however, was not used commercially and was not fully noticed except by the food industry. In 1910, however, the first company was established in Great Britain, which for many years was very recognizable thanks to the production of heat exchangers, the APV company. In some old installations, you can still find exchangers under this brand. The company began to produce exchangers which were dedicated to pasteurization, but also to brewing, where it was applied to cool the beer wort quickly and economically. A plate heat exchanger, which APV patented in 1923, is considered to be the date of the beginning of plate heat exchangers. That is, these devices took the form that they have today. Until World War II, these were imperfect devices. At the same time, however, work was underway to improve them, the more so because they found an increasing spectrum of applications along with the developing industry. Entrepreneurs from the USA, Germany, Great Britain, and Scandinavia made great contributions to their improvement. Next slide, please. The first literature review, a water-to-water preheater and a steam-to-water network, temperature dynamics. This experiment consisted of a double pipe preheater connected to a heater with condensing steam in the annals. Hot water exiting the heater was used to warm the cold water supply. The two exchangers were connected via tubing. The preheater could be operated in concurrent or counter-current modes by changing the direction of the flow in the annals. System dynamics were observed for changes in steam temperature and water flow rates. Analytical solutions were derived for the integrated equipment, subject to the preheater in a concurrent configuration with equal water velocities. Solutions were solved sequentially in time utilizing MathCAD to simulate dynamic responses. Predictions were based solely on the supply water's temperature, steam temperature dynamics, heat transfer constants, and equipment dimensions. Temperatures at the exit and entrance of each heat exchanger were calculated first. After these dynamic temperature profiles were determined, interior temperatures were then evaluated. Results illustrate effects and complexities introduced by process integration. For both concurrent and countercurrent configurations, the time increment required to reach steady state after a change-inducing dynamic behavior is significantly longer than the sum of the residence times of the individual unit operations. Local temperature maxima and minima were observed during concurrent flow conditions. Simulations demonstrated that these are functions of delays associated with the equipment network, including delays associated with connective tubing. The dynamic simulation of the system adequately predicted experimental data, but could be improved by incorporating an energy balance for the inner tube wall of the heat exchangers. The addition of the tube wall to the model would increase the apparent order of the temperature response and will reduce the simulation lead relative to data. Next slide, please. Our second literature review, parametric system identification and robust controller design for a liquid-to-liquid heat exchanger system. This study provides a step-by-step analysis of a parametric system identification procedure, which provides a single input, single output, linear time invariant time delay model of a liquid-to-liquid heat exchanger system. There are different types of heat exchangers, such as a recuperative type, regenerative type, and evaporative type. In the recuperative type heat exchanger, the fluid exchange heat on either side of the dividing wall. The recuperative heat exchanger may be further designed to act in different modes, such as parallel flow, counterflow, or cross flow. Among the three, counterflow type is the best suited for application because in this configuration, the thermal stress is minimized and the uniform temperature distribution provides a uniform rate of heat transfer. In system identification, the first step is to collect open loop or closed loop experimental data from the plant. To gather this data from the plant, an optimal experiment had to be designed. The optimal input design depends mainly on the behavior of the system. In practical cases, there are different constraints in the system, and most of the available literature consider the Gaussian noise while designing the optimal experiment. However, in a real-world environment, non-Gaussian noise occurs frequently. To achieve the control objectives of the system, a controller is designed. A classical PID controller is the first choice of engineers due to its simplicity and proven track record. In this study, the classical PID controller is used to control the temperature of outlet liquid of the liquid to liquid heat exchanger. The PID controller has three tuning parameters such as KP, KI, and KD. There are many tuning methods available, but this experience uses Ziegler-Nichols method to obtain the controller parameters. To evaluate the performance of the controller, three different conditions such as set point regulation, load disturbance rejection, and set point tracking have been considered. The designed robust PID controller meets the control objective with moderate success under the three different operating conditions. The load disturbance rejection and set point tracking provides slightly higher overshoot and settling time. In the set point regulation mode, the overshoot and settling time are minima. In this case, provides the best possible result. Next slide, please.
So as to the motivation, when it comes to a vehicle HVAC system, it is one of the major keys that take part in fuel consumption and exhaust emissions. How that makes a difference is with the amount of heat and excess that is being shared with the environment during processes of manual or automatic control of temperature inside the cabin. The environment is basically affected directly due to these processes and fuel emissions, which also takes a load on the abilities of the engines, making it work harder than it really should with more effort. And with a moist airflow model, we can successfully interpret the conditioning responses needed for these changes. Next slide, please. By changing parameters and creating a simulated model in one of two methods, a predefined system input or a manual system input, we can understand the brief conditions throughout average drive cycles and during distinctive city/highway driving patterns, which will give us further insight on how to optimize on the critical understanding of the requirements behind increased performance of an HVAC system and concurrently optimize AC systems designs inside the general vehicle design nowadays. Next slide, please.
The purpose of this project is to model moist airflow in a vehicle heating, ventilation, and air conditioning system using Simscape. When humidity is very high, the AC system expands most of this effort, removing the moisture out from the air. This decreases the overall performance of the AC system. The HVAC system performance has a direct result on fuel consumption and exhaust emissions. Studies have revealed that during the SCO3 drive test, the influence of the HVAC system over an assortment of light-duty travel vehicles increased fuel consumption by 28%, CO emissions by 71%, NO2 emissions by 81%, and non-methane hydrocarbons by 30%. By modeling the moist airflow in a vehicle system, we will be able to detect how much or volume within the vehicle is exchanging heat with the external environment, giving us insight onto how to fully configure system inputs predefined or manual, plot psychometric chart for visualizing cabin air, plot condensation and evaporator, and explore simulation resulting using SSC Explore. Thank you for your attention.
Thank you.